Hi, this is a pre-lab talk about the theory and calculations behind the Chemistry 102 experiment on analysis of vinegar. So first off, let me tell you a little bit about vinegar. It's a solution of an organic acid, a carboxylic acid. Those are sort of usually synonymous. It's a solution of acetic acid. And we're going to have, it's usually about 5% acetic acid in water. And acetic acid is naturally occurring. It gets produced in sort of a number of different places in living organisms. In fermentation is one common way. One thing to pay attention, unlike the mineral acids like nitric acid or phosphoric or sulfuric acid, some of those have more than one hydrogens, phosphoric acid, sulfuric acid, and more than one of those hydrogens are, usually a number of them, are acidic hydrogens. That just means that that hydrogen can leave the acid as an H+. In acetic acid, we can see that there's 4 hydrogens total, but the 3 hydrogens attached to the carbon, they're kind of very tightly bound, and because of how the carbons and the hydrogens behave, and in contrast, how the oxygen to hydrogen and how those are bonded together, only the hydrogen attached to the oxygen is acidic. So there's only one acidic hydrogen on acetic acid, and therefore when we react it with sodium hydroxide, it reacts in a 1-to-1 stoichiometry. So for every 1 molecule of acetic acid, it'll react with 1 molecule of sodium hydroxide. And we're going to use that fact in the titration. We're going to take a known concentration of sodium hydroxide, and based off the concentration and the volume of sodium hydroxide, and then based off how much of the acetic acid solution, the volume, we can find the concentration of acetic acid in the vinegar sample. So one of the important points about this is that we have to know when we have combined equal amounts of the acetic acid and the sodium hydroxide. And the figure here is showing something called a titration curve, and it plots pH as different volumes of sodium hydroxide were added. I just found this figure online. It doesn't relate to the experiment that we're doing in any particular way, but it is a kind of a good representation of what's going on over the course of the titration. So we aren't going to have a titration curve like this from the data that were gotten. This was the people who made this. They used a pH electrode to measure the pH as they added small amounts of sodium hydroxide, and so that's all those little data points. They are showing a pH and the volume of sodium hydroxide that had been added to the titration. What we're interested in is finding the equivalence point, which is the middle of this curve. It's the little red dot there. So the equivalence point is when we've sort of added equal number of moles of acetic acid and sodium hydroxide. So we need to be able to know where that little red dot is. Now, if we have a pH meter and we do it just like these guys did their experiment, that would be pretty easy. We just look for the position sort of right in the middle of this kind of S-shaped curve. Sometimes it's called a sigmoidal curve, and just by looking at it, you can tell pretty closely about where the center of the S shape is. So we don't have a pH meter. We're going to use instead an indicator. An indicator changes color as pH changes, and we have to choose an indicator that changes color near that equivalence point. And it doesn't do it right exactly at the equivalence point, but it does pretty close. That just means that sometimes you'll see this distinction between an equivalence point. That's the actual spot where the moles of acetic acid and sodium hydroxide are equal to each other. and an endpoint, which is when we observe a color change in the solution due to the indicator changing color, and that will be, at a slightly different pH than the equivalence point, but it'll be pretty close. So the procedure we're going to go through is, it's actually not just the analysis of the acetic acid and vinegar using sodium hydroxide. We actually have to do kind of a pre-experiment. So the problem is that if you go out and buy solid sodium hydroxide, and you can do that, it comes in these little pellets, they're called. A lot of times that is somewhat contaminated with carbonate compounds. Also, it's very hygroscopic. It can pull water out of there. Hygroscopic just means water-loving, kind of, and it'll pull water out of the air. And therefore, when you measure out the solid sodium hydroxide, you don't know if you're just weighing out sodium hydroxide or if you're weighing out carbonate impurities or water. And therefore, you can't trust the mass of the solid sodium hydroxide real well. It's a little bit uncertain. And so instead, we're going to do a standardization method or procedure. So standardization just means you're going to fix, or in some way, by referring to a reference substance, you're going to fix the concentration. So we're going to standardize the sodium hydroxide solution with a known solution of hydrochloric acid, and then we're going to use the concentration from that step to figure out the concentration of acetic acid and vinegar. So the calculations, the key point that we want to know is that at the color change, the moles of the hydronium, H3O plus, are equal to the moles of the hydroxide. So if we can calculate, if we can set up an equation where we know all the values except one, we can solve for that one unknown, and by using this equality that the moles of H3O plus are equal to the moles of hydroxide. So in the first part of the experiment with sodium hydroxide standardization, we're going to say the moles of HCl are equal to the moles of NaOH. And here in all the experiments, we don't have to worry about the H3O plus and the hydroxide that are produced from water. Those are there, but they're at small enough concentrations they aren't significant. In the second part, for the vinegar analysis, we can say the moles of acetic acid, CH3COOH, are equal to the moles of sodium hydroxide. So how are we going to find the moles? Well, the moles of NaOH are equal to the molarity of NaOH times the volume of NaOH. Now, normally we'd have to say, the volume should be in liters if we want moles, but it turns out we can use milliliters in these calculations, and that's because you can see we set up this equation that says molarity of NaOH times volume of NaOH is equal to molarity of HCl times volume of HCl. Well, if both the volumes are in milliliters instead of liters, their units will cancel out as we rearrange the equation. And so it doesn't so much matter what the units are of the volume. They just have to be the same for the NaOH and the HCl. So this little equality between molarity NaOH times volume NaOH is equal to molarity of HCl times volume HCl. That's true only at the equivalence point, which we're approximating as when the color changes. Now, using a burette, which is a method of measuring out different volumes of liquid, we'll know the volume of NaOH. You're going to be told the molarity of the HCl, and you're going to use a specified volume of HCl in the sample you make up. And therefore, we can solve for the molarity of NaOH. In the second part of the experiment, we're going to do really something similar, except now we use acetic acid, the vinegar, instead of the HCl. And now we know the molarity of NaOH. It's the molarity of the acetic acid that we don't know. But we can set it up very much the same. Now we know that volume of NaOH from burette. Now we know the molarity of NaOH from the first experiment, from what we just did, and then you can we'll measure out a known volume of acetic acid, and so we can solve for the molarity of acetic acid. And that's what we want to solve for. So in summary, these acid-base titrations are a really simple way to analyze solutions. You need a way to observe the equivalence point, but a lot of times we use indicators, which are really cheap and easy to do. And one big idea is that the moles of the acid and base are going to be equal at the equivalence point. In our experiment, it turned out that did mean that the moles of acid and the moles of base were equal, because the sodium hydroxide the sodium hydroxide only provides one hydroxide, OH minus, and the acetic acid and the HCl, they're monoprotic. They only provide one H plus, and so everything reacts 1 to 1. All right, good luck.